Well, finally, in 3.6, I'm not going to add any new derivative rules to you. We can take a break from some derivative rules for now. But the bad side of that is we're going to look at a bunch of application problems with derivatives. And I touched on it a couple of sections ago with talking about derivatives representing a rate of change. And I have people ask me all of the time, and it's usually people who didn't take much math or didn't go really high in their math classes. When I tell them that I teach math, and in particular I teach calculus and differential equations, and they say, well, I've gone my whole life without knowing that stuff and I'm perfectly fine. What's really the point of calculus? Calculus is the mathematics of change. And if everything in the world is constantly changing, so if you truly want to analyze how something works and be able to dissect it and study it and make improvements upon it or recreate it or anything like that, you have to know calculus. So calculus is the mathematics of change. And derivative is how something is changing. So in these application problems, we're going to see a lot of talk about change, rates of change, and then in specific application problems, they call it something a little bit different based on what exactly they're talking about in that particular problem. One of the most common applications that you see in math textbooks and used a lot in science classes and physics and astronomy, things like that, are velocity and acceleration. So one of the things that we like to do, so these are almost all going to be applications. So let's say, let me give you a little bit here first. Calculus, and that is not how you spell calculus, is the mathematics of change. With the velocity and acceleration applications, it's very common for us to use t as the variable to represent time. So if we call s of t a position function, so this is describing our position at time t, then the derivative of position, which we also could call v of t, is velocity at time t. And our second derivative, which is the derivative of our first derivative, we might call a of t, which is acceleration at time t. Acceleration describes how our velocity is changing. Each derivative tells how the previous one is changing. So this notation is just using the apostrophes, but if we use the other notation with the fractions, that will help us with the units, because I know some of our MyLabs Plus problems ask us about units. So let me touch on that a little bit before we actually look at an example. So let's say s of t is position in miles after t hours. So I can plug in 3 hours and it will tell me how many miles I've gone. I can plug in 10 hours, it'll tell me how many miles I've gone. I can plug in 40 hours, it'll tell me how many miles I've gone. So this s of t just tells me my position in relation to some sort of reference point at a certain time. If we take the derivative of that, and I'm just going to do a different notation. So ds dt. That's just another notation for derivative. So remember, we said the derivative of position is velocity. So this is another way to write velocity. And look at how we've written this. We've got s in the top, and we've got t in the bottom. So s is being measured in miles. T is being measured in hours. So velocity is being measured now in miles per hour. So this is change in position measured in miles per hour. And I figured that out just based on where my variables are in the notation. I have s in the top and I have t in the bottom. And then my second derivative, d2s over dt2. Now remember, those 2's don't represent exponents. They represent superscripts, meaning second derivative. We could also write this as take the second derivative of your s function. So again, we have s in the top, but we've got t twice in the bottom. We don't have s twice in the top. The s is only there once, but the t is twice in the bottom. So this is change in velocity. Every time we go out a derivative, it describes the change in the previous one. So this is change in velocity. And I probably should have wrote acceleration. I'll add that in just a second. And it's measured in miles per hour squared. Instead of miles per hour squared, sometimes I've seen in physics class some problems call it miles per hour and then per hour again, because we could separate those derivative notations and say dt of s of t. So each of the dt's means per hour. So s is measured in miles. So this first one is miles per hour. So I want to know how my position is changing in miles per hour. So that's velocity. And then I want to know how velocity is changing. The velocity is measured in miles per hour, and I want to know how that is changing per hour. So the acceleration unit is a little bit tricky because of the hours squared, but it could also be miles per hour per hour. Either one of them is correct. You're most likely going to see the squared more, but I have seen the per hour before as well. But I can tell the units just based on the position of the variables in my derivative. So I want to look at an example that asks us to find velocity, position, acceleration. I want to add one thing to this though. Velocity has two parts to it technically. Our position can change two different ways. It can change because we're speeding up and slowing down, or it can change because we're changing direction. So we could be going forwards and backwards. So there's actually two parts to the velocity. There's a number component telling how fast we're going, but also the sign on the number, whether it's positive or negative, is important. And sometimes we don't care what direction we're going. And if we don't care what direction we're going, we just care about the number portion, then that is speed. So technically, velocity and speed are not the same thing, but they are related. Speed is just the magnitude of velocity. It's just the number portion of the velocity, and it disregards the positive negative part. Speed is the magnitude or the absolute value of the velocity. So we disregard direction, which in most of these is just positive or negative, up or down, left or right. We just want the number portion of it. So I've copied a problem out of MyLabs Plus that I'm going to paste here, or I'm going to attempt to. I don't know if I've ever done this before. Let's see. Oh, yes. That was easy. So it's kind of small. Sorry about that. You should have one really similar to this in your homework. We want to suppose the position of an object moving horizontally after t seconds is given by the following function, s equals f of t, where s is measured in feet, s is greater than 0, corresponding to positions right of the origin. So if s is positive, we're moving to the right. If s is negative, we're moving to the left. We want to graph the position function, find and graph the velocity function, and determine when is the object stationary, when is it moving to the right, and when is it moving to the left. Determine the velocity and acceleration of the object at t equals 1. Determine the acceleration of the object when its velocity is 0, and on what intervals is the speed increasing. So that's a lot of stuff, but you have a homework problem just like this one. So I thought it was important that we go through some of these homework problems together. So I'm going to graph this in Desmos, and you certainly can as well, because in the homework it's just matching the graphs. You're never going to have to graph these out by hand from scratch. And the nice thing about Desmos is they have a derivative graphing tool. So our function is, oops, I'm just going to use x instead of t. X cubed minus 12x. Let me go back here. Squared plus 45x. And they just want between 0 and 7. X is between 0 and 7. So we can adjust our window over here using graph settings. And I'm not sure what the y's are that are going to go with that, but you can always change this to a table and see. It looks like the y values are going really, really negative. So all I did is I hit this little widget here. I'm sure that's not really what it is. But at 0, the function's at 0. At 1, it's at negative 56. At 2, it's at negative 30. Ah! So we're going to have to go down really, really low on our y-axis. I'm going to say negative 200 just to be safe. And then go up to positive 200. Nice. So it looks pretty good. Not too bad. We probably don't need to go negative 200 to positive 200, but that was just a guess. We'd probably go between, say, negative 50 and positive 100 now that I can see the actual graph. That looks a little better. So one of the first things it asks you to do is just graph the position function. So on the x-axis or the t-axis, that is time. It's just describing time. And then on the vertical axis, it's our position with respect to the origin. So after 1 hour or 1 minute or 1 second, I'm not sure if it gave us any units here. T is measured in seconds, S is measured in feet. So after 1 second, we've moved almost 35 feet. After 2 seconds, we're 50 feet. After 3 seconds, we're almost 55 feet. 4 seconds, it looks like we've come back a little bit. We're about 52 feet. 5 seconds, 50 feet. 6 seconds, back up to 55 feet. 7 seconds, it looks like we're up at 70 feet. So we started to move away again. So you can look at those Y values and see how they fluctuate up and down. And you can tell, like, we're moving away from something because the Y values are getting bigger. And then we're moving back towards it because the Y values get smaller. And then we start to move away again. So our starting point is like the x-axis. Our starting point isn't exactly the origin because we're always going to be moving away from the origin because we're counting out a time interval. So our time interval is always going to move away as we go along the horizontal axis. But always do it in relation to that horizontal axis. So this distance is how far we've gone at that time. This distance is how far we are now. This distance is how far we are now. So we're moving farther and farther away, but then you look over here, we're not as far, so we must have backtracked a little bit. And then go over here and up, we've gained some distance. So we've turned ourselves back around and started moving away again. And over here we're even farther away. So we've continued to move away again. So always when you're deciding which direction you're moving, whether you're moving forwards or backwards, always compare it to the x-axis to decide if you're moving forwards or backwards. And I'm actually going to change my X here because I want to see a little bit more than 0 to 7. That way 0 and 7 are like clearly visible in my screen. That makes it a little easier. So the first task was just to graph your position function. So graphing the position function we can do in Desmos. Part B says find and graph the velocity function. So the velocity function is the derivative. So v of t is f prime of t. So that's just our normal derivative. This is a pretty easy function, nothing crazy. in terms of derivative rules, we just have to do the power rule on each piece. That's going to be 3t squared minus 24t plus 45. So when we graph this, we have two options, and I'm going to show you both of them. Since the derivative was really easy to find on our own, we can just type in 3t squared minus 24t plus 45. And I'm going to type that in for the second one so I can see them both on the same graph. Your other option is Desmos has a derivative graphing function. So under functions, you can go to miscellaneous, and there is a derivative operator there. It says ddx. You can tell it to graph a derivative. So, and you don't have to find the derivative on your own. It'll find and graph the derivative for you. So you can tell it, graph the derivative of x cubed minus 12x squared plus 45x. And look, it fell right on top of the purple graph because we already found the derivative on our own and graphed it. So if you don't necessarily need to find the derivative, or if the derivative is really, really tricky and you just need to know the graph or some points on the graph, Desmos does have that derivative graphing option. It's under functions and miscellaneous, and they have the ddx there. So that's an option. But I'm going to clear this out because we already have it in purple. So there is our derivative graph, the purple graph. So we found our velocity function and we graphed our velocity function. It says, when is the object stationary? So stationary means not moving. So no change in position. A lot of these application problems, they're going to give you these English words, and you need to think about what does that mean and what does it mean in terms of math and the things that I'm doing and I'm trying to solve for. So stationary means not moving, means not changing position, if we're not moving and we're not changing position, well, what is measuring our change in position? Remember, change is derivative. So if we have no change in position, then we have no derivative of position. That means our derivative of position is 0. That means our velocity function is 0. Oops. They're asking us, when does velocity equal 0? The object is stationary when velocity equals 0. So we're going to look at this graph. Our velocity graph is the purple graph because that was our derivative. And velocity is equal 0 when it is crossing the x-axis. So it's crossing the x-axis at t equals 3 and t equals 5. It says, when is it moving to the right and when is it moving to the left? Well, if it's moving to the right, That means it's moving away from the origin. That means it is gaining position. It's gaining distance. That means its change in position is positive. That means v of t is greater than 0. It's moving to the left when it's backtracking, and it's moving back towards its starting spot. And we're losing position. And that is when our velocity is negative. Since we have the graph of velocity here, we can just look and see when the purple graph has positive values and when it has negative values, when it's above the x-axis and when it's below the x-axis. So the purple graph, our velocity graph, our derivative graph, it's above the x-axis from 0 to 3 and then from 5 to 7. Remember, we only care about what's going on between 0 to 7. That was part of the directions of the problem. So 0 to 3 and 5 to 7. I'm not including 3 and 5 because at 3 and 5 it's stationary. And then it's moving to the left. If you look back at your graph, at that little piece right here, it's below the x-axis. That's when your velocity has negative values. That's when we're moving back to the left. And if you look at the original function, that's when it's going back down. That's when it's getting closer to the x-axis. We're losing position in those spots. It's coming back towards the x-axis there. So in that little piece between 3 and 5, our velocity has negative values because we're moving back towards the left. So again, I'm going to use parentheses because it's not moving to the left at 3 or at 5, it's between 3 and 5. We've already said at 3 and at 5, it's stationary. Part C says determine the velocity and acceleration of the object at t equals 1. Well, we've got a velocity equation. All we have to do is plug in 1. So for part C, our velocity function we said was 3t squared minus 24t plus 45. 3t squared minus 24t plus 45. And remember, acceleration is the next derivative, so 6t minus 24. We want to know what's going on at t equals 1. So all we have to do is plug in t equals 1. So v at 1 is going to be, so replace all the t's with 1, I get 3 minus 24 plus 45, which is 24. And our units, remember velocity is ds dt. S is in feet, t is in seconds. So this is going to be feet per second. And then a at 1 is going to be 6 minus 24, which is negative 18. And that's going to be, that is another derivative on velocity. So it's with respect to t again. So that's feet per second squared. Negative 18 feet per second squared. Now if you look at your v graph, if you look at your derivative graph at 1, we should see that it's at 24 approximately. So the purple graph was our velocity graph, and it does look like at 1, it's approximately at 24. And you can actually touch it with your mouse and see that it's at 124. Now we don't have our acceleration graph here, but we could certainly put it on if we want to. The next derivative is really easy to find. It's just 6x minus 24, we said. And if we wanted to know what was happening at 1, we can just go down and touch it with our mouse. and it's negative 18, it says. So we got those right. So we've got velocity and acceleration at time 1. Determine the acceleration of the object when its velocity is 0. So we've already figured out when velocity is 0. That's t equals 3 and t equals 5. That's when the object is stationary at t equals 3 and t equals 5. So in part D here, they're just wanting us to find a of 3 and a of 5. Well, we already have an a function. It's 16 minus 24. They just want us to plug in 3 and 5. So that's 18 minus 24, which is negative 6, and 30 minus 24, which is positive 6. And these guys are in feet per second squared. So we already knew when it was going to have velocity 0, and we already had an acceleration function. We just had to put those two ideas together and do a calculation. And again, we can look back at our graph, and here is when velocity is 0, and I can trace that down to my acceleration graph, and it says at 3, my acceleration is negative 6. And then here is my velocity graph being 0, and I can trace it up to my acceleration graph, and it says positive 6. And I think we've got one more part to this one. Yep. Part E says, on what intervals is the speed increasing? Is the speed increasing? So we said earlier that speed is the absolute value of velocity. And we just want to know when it is increasing. So we just need to think back to what we learned in algebra class about when a graph is increasing or decreasing. So a graph is increasing when we look at it from left to right and it's going up. So we're just going to graph our speed function and look to see when it's going up. So our velocity was 3x squared minus 24x plus 45. We just want to know what the absolute value of that function is. So I'm just using my absolute value bars, and I'm going to type that entire function in there. 3x squared minus 24x plus 45. And it changes it just a tiny bit. So this is now an orange graph. I'm going to see if it's going to let me change the color of that. I don't know if it's gonna. Nope. Oh well. So it's like a dark orange graph. So really all it did is it pulled that purple piece that went below the x-axis and it kind of reflected it up. We want to know when speed is increasing. So I want to know on this dark orange graph, what parts of the dark orange graph are increasing. So if you trace the dark orange graph from left to right, we want to know what pieces are increasing. But remember, we're only concerned from 0 to 7 because that was stated in the directions of the problem from 0 to 7. So start at 0 and we're going down. So that piece is decreasing. When we get to 3, we just very slightly are increasing from 3 to 4. And then we start going down again from 4 to 5. And then from 5 up forever, we're increasing. But we're going to stop at 7. Because the problem says stop at 7. So we've got this little increasing piece from 3 to 4, and then we have an increasing piece from 5 to 7. So all we're doing to get the speed graph is doing the absolute value of our velocity graph. And then it's increasing anytime the function is going up from left to right. Anytime it's going up from left to right. So that was happening between 3 and 4. And we always use parentheses for these intervals unless we're using an endpoint. So 3 to 4 and 5 to 7. And I'm going to use a bracket on the 7 because the 7 is an endpoint. Okay, so all sorts of different information just from a position function. All we were given at the beginning was a position function, and we've figured out all sorts of stuff about its velocity and its speed and its acceleration, when it's stationary, when it's moving to the right, when it's moving to the left, all sorts of great stuff. So I want to look at one more example with you. This one's completely different, asks us to do some completely different things as well. And this one is more of like a business application. And you have one just like this again in your homework. And I think it might be the last one. It says, let C of X represent the cost of producing X items, and little p of X be the sale price per item if X items are sold. The profit, capital P of X, of selling X items is capital P of X equals X times little p of X minus C of X. So it sounds confusing, but we're just going to plug stuff into all of those spots and create a function. And really all that equation says is revenue minus costs. The average profit per item when X items are sold is P of X divided by X. That's the average profit. And the marginal profit is dP dx. Now that's derivative notation. So the derivative of the profit function is called marginal profit. The marginal profit approximates the profit obtained by selling one more item, given that X items have already been sold. Consider the following cost function, C, and price function, P. And they've got some things they want us to do. Find the profit function. So they tell us how to set up the profit function, and they give us all the little pieces that we need. So big P of X, our profit function, is X times little p of X, and they give us our little p of X here, minus C of X, which is cost function, which is here. So part A is just set up your function. So big P of X is X times 200 minus our cost function, which is negative 0.03 x squared plus 90x plus 600. And we're going to simplify this sum. So this is just 200x. I'm going to distribute that negative plus 0.03x squared minus 90x minus 600. We can combine some like terms. And my final answer here for my profit function is 300th x squared. These guys can get put together. 200 minus 90 is 110. So 110x minus 600. So all algebra so far, all algebra. So we've got our profit function. Find the average profit function and marginal profit function. So average profit, they say, average profit is your profit function divided by X. So in part B, average profit is P of X over X. So we just need to take that previous answer and divide everything by X. So 0.03x squared plus 110x minus 600 all over x. And again, we can simplify it a little bit. Two of those terms we can pull an x out of, 0.03x plus 110, but the 600 we can't pull an x out of, so I leave that as minus 600 over x. So that is our average profit. marginal profit says marginal profit is derivative. dp dx is the notation for derivative. The derivative of p with respect to x, or p prime of x. So here's our original p. We just need to go through and take the derivative. So just do the power rule. We get 0.06x plus 110. That is our marginal profit. Part C says find the average profit and marginal profit if x equals A units have been sold, and they give us an A value here. A is 1,000. So just some algebra. We've already figured out the functions. Now we just need to plug 1,000 into them. So P of 1,000 over 1,000. That was our average profit. Now I've already simplified that function, so I'm just plugging 1,000 into there. So 0.03 times 1,000 plus 110 minus 600 over 1,000. And we will simplify that. And I've got 139.40. P prime at 1,000, which is marginal profit, we're going to plug 1,000 into. I get 170. And then for part D, interpret the meaning of the values obtained in part C. So I actually want us to talk about what these two mean. Average profit per item when X items are sold. So if we sell 1,000 items, so average profit of 139.40 means that if we sell 1,000 items, that's what the 1,000 means. If we sell 1,000 items, and they did tell us how much they cost each. The little p of x was how much they each cost. So we're selling them for $200 a piece. Average profit of $139.40 means that if we sell 1,000 items for $200 each, $139.40 of that 200 is profit on average. Now, if we sold less items or more items, that number might change because of fixed costs. So the more items you sell, the farther out we can spread the fixed costs usually, and the more profit we can make. So fixed costs, if you haven't taken an economics class, are things like rent, You've got to pay rent for your facilities, whether you produce something or not. So if you pay a month's rent and you produce nothing, you still have to pay the rent. Or you can pay a month's rent and you can produce a million things, but your rent is still the same. So it's a fixed cost. So we can spread that rent out over a million things and make a lot of profit, or we can spread it out over nothing and lose a lot of money because we still had to pay rent. So the average profit means that we sell 1,000 items for 200 each, and we get to actually keep 139.40 out of that 200. So the marginal profit, though, isn't an average of all of them. The marginal profit is only referring to how much we'll make on the very next one that we produce and sell. So a marginal profit of 170 means that if we sell 1,000 items for 200 each, we could expect to profit $170 on the next item sold. This is an important thing for businesses to know, because increasing production does not always increase profits. There's always an optimal production level. You can't just increase production to an unlimited amount. So you want to know if increasing is worth it. So you want to know if $170 of profit is worth increasing production or not. So it's a good thing to know what that next, if you produced one more, how much are you going to make off it? So that number might be really small. So you're going to say, nope, it's not worth it. This is our optimal level right now. We're going to stay where we're at. Or you might do the marginal profit and say, wow, that's a lot of money. If we just produce a few more, we're going to make a lot of money. We need to increase production some. So marginal profit is just how much profit you're going to make on if you made made and sold just one more item above your current production level. So currently we're at 1,000. So if your 1,001st item, you should expect to profit $170 off of it. So that's the difference between average profit, where it's spread out over all of those 1,000 items, and marginal profit just means what do we expect to make on the next item.